Okay, so now we're going to look at acids and bases, those which will change the pH of water. And in the first three videos that I sent out to you earlier about the concepts of acids and bases, we talked about strong acids and weak acids. And we're going to start out with strong acids. And one thing we're going to assume about strong acids is essentially they 100% dissociate. Okay, so there's no reverse reaction. The reaction goes completely to the right. Um, now, just like any reaction, all reactions are are reversible, but essentially it's so this reaction is so far it's such large to the right that we don't even effectively look at the reversible reactions. And here's a list of strong acids, and it'll make our life easier in terms of figuring out OH and H plus and pH. Therefore, pH. Therefore, if you know 1 mole of these guys, all right, and we'll talk about this guy here. It's a little special case. Uh, is that if you have 1 mole, there's 1 mole of H plus for every 1 mole of acid, especially for these guys right here. This double one here we'll talk about later. But so if you have 0.04 molar, what is it, perchloric acid, and you put it in water, what's going to happen is it's completely dissociate. The H pluses come off. There's 1 mole of H plus for every 1 mole of perchloric acid. Therefore, if you have 0.04 molar perchloric acid, you're going to form 0.04 molar of hydrogen ion. And then simply to figure out the pH, you take the minus log of the hydrogen ion or hydronium, and the answer is 1.4. So that's conceptually, hopefully you'll think it out. We'll formalize it in here. Okay, now if we look at bases, you have, these are strong bases, and it kind of notices that what they all in common, they all are hydroxides. Therefore, these are all areneous bases. Um, strong bases, I should have said. So again, for every 1 mole of these guys, if you have 1 mole of sodium hydroxide, you'll release 1 mole of hydroxide or 1 mole of base. For these guys down here, you have 2 moles of hydroxide are attached to 1 mole of your metal ion, and so, for instance, if you have 1 mole of calcium hydroxide, you will produce 2 moles of hydroxide. Okay, so let's just take a look at an example of that. So if you have 0.0001 mole, one molar of calcium hydroxide, what happens, it splits up into calcium and 2 hydroxides. So this is going to determine how much hydroxide you have, and therefore your H plus concentration and your pH. So your OH concentration is 0.00022, or twice this number here. You can figure out the PO, just taking the minus log. Then the pH is going to be 14 minus the PO, and you get 10.344. And then to figure out the hydrogen ion concentration, you just raise that to the 10.3334, and you get this for your molarity of hydronium or hydrogen ion. Okay, so now what we're going to do is we're going to formalize it into an ice table. So your initial change and equilibrium, and we use these when we talk about equilibrium. And hopefully you guys will get that assignment in to me soon. Like a couple of you did. It's what we did before break. And so if you start off 0.1 molar HCl, so your initial is 0.1 molar HCl, and none of the product, and then once you put in the product, what happens is this guy completely disappears. It turns into product. So all 0.1 gets turned into product. You really don't have to worry about this. So so you form 0.1 molar of the H plus. Okay, then you add your your change to your initial, and you get 0.1. And then the pH is going to be the minus log of the H plus, 0.1, and your answer is 1. Okay, we can do the same thing with the base. So your initial concentration 0.5. Put in water, it completely dissociates. 0.5 and 0.5 times 2, because you have two hydroxides. So your change, so there's none of the original calcium hydroxide. There's 0.5 molar of the calcium that's formed, and 0.5 times 2 amount of molar of your base, or so it's 1 molar. So you figure out your PO minus 1 of a minus log of 1, which is equal to 0. Log of 1 is always 0. And then the pH is going to be rearrange this equation, and it's going to be 14 minus PO, or this is going to be have a pH of 14, which is really basic. Okay, so let's get into weak acids and weak bases. And now what we have to do is we're going to have to be more careful about how these guys split up, since weak acids and weak bases don't completely split up. So if you start out with 2 moles of acid, you don't necessarily end up with 2 moles of H plus. Okay, so and we're going to have some sort of quantitative value to help us figure that out, and we'll use that. So so we have these two equations, and we're going to look at them kind of in a minute, but let's take a look at this guy. This is acetic acid, and when you put it in water, it dissociates an acetate and hydronium, but it also comes back, and there is a ratio of how much goes back and forth, and we're going to be talking about that. And then the same can be said for all of these. And so what we're going to end up doing is we're going to end up having an equilibrium expression for each one of these equations, showing how much product there is per reactant. Okay, so let's set that up. So here's the general equation. So acid plus water gives me conjugate acid and hydronium ion, in this case right here. So our equilibrium expression is going to be our product over our reactant. And because the water is such a high concentration compared to the rest of the species, we can pull it out here and put it with the Kc, because it's basically not going to change. And so here it is. And then we can just wrap this up into one constant, call it Ka. And K is what we're going to be looking at from now, and it's going to equal to the conjugate acid times the H plus over the amount of acid that we started out with. Okay, we can simplify it as simply the acid splitting up into its conjugate acid and H plus, and rewrite the equation as this. Either one is fine. And then what we can do is, if we have this value, we can figure out a pKa value, and we'll see that it may be easier to look at in terms, because we'll see that this number will end up being a very small number, usually like 10 to the minus fourth or something. So it's nice to have it in a value that doesn't use an exponent. And then if you do have this, you can you can find the equilibrium, the acid dissociation constant, by simply just going 10 to the minus pKa. So we're going to be using this equation quite a bit from here on in. And here's some values is of Kas and their associated pKas. And so Okay, and so this is ordered in terms of strong acids to weak acids, and let's take a look at that. So and the way that I kind of have it in my head and is it kind of works kind of like pH, and it's not. I mean, you can make the relation, but you know that low pH means you have higher acidity. Lower pKa means it's a stronger acid for kind of the same reason. So I kind of associate those two sometimes if I want to remember which. If I have given a pKa, I go, oh, when I have a low pH, that means it's acidic. Okay, or more acid, and I kind of use that as help. It's not necessarily. It's just a way to help remember. But let's formalize that a little bit. So what I want to do is look at iodic acid and compare it to cyanic acid. So I said that these guys at the higher have higher are the stronger acids than the ones at the bottom. So let's take a look at why that is. So essentially, equilibrium constants compare the amount of product per reactant. So if the K is product over reactant. So if we look at the Kas for iodic acid, the Ka is 1.7 times 10 to the minus first. And if you look at that number, what that number is that means there's one product for every 58 reactants. That's one way to look at it. And it's a little bit, it's more than that, but that's the simplest way to look at it. Now, if you look at this cyanic acid, okay, it has 2 times 10 to minus 4th as its Ka. And what that means is that one product is formed for every 1,000 reactants. Okay, so that suggests is that there's not a lot of product being formed here compared to this guy here. This guy here is forming almost 100 times more product than the cyanic acid. Okay, so that means more of this is going to the right, and therefore it's a stronger acid because it's dissociating, having more of the acid dissociate. Okay, so that's a way to kind of think about it. Okay, so won't worry about that a lot, but it's good to know what those numbers mean especially when you want to compare different acids with each other. Okay, so let's do a problem here. What I want to know is the pKa of HF if the Ka of 3.5 of this HF is 3.5 times 10 to the minus 4th. So you can write out the equations as such. But it's so the pKa is simply going to be minus log of Ka. So minus log Ka is 3.46. You don't really need to do all this, but it's just you can just show it. So the pKa is equal to minus log Ka minus log Ka. All right. Okay, so reaction of weak base in water. And so again, what we could do is you have the so that what we're doing looking at here is that the is now this is acetate, and when you add it to water, what it will do is it'll grab a hold of an H and it'll form acetic acid and OH. And so what we can do is we can write that equation. So this is a base reaction where base reacts with water instead of acid react with water. And we can go through it, but basically what you're going to end up with is the product. Okay, the conjugate acid times the hydroxide all over the base constant. And you can get pKb, which is minus log Kb. And then if you want to get Kb back, what you do is you just take it minus Kb. And so it's a similar equation as the Ka, but looks at Kb. All right, so let's look at what is a pKb. if the Kb is 1.7 times 10 to the minus 9th. And so you can set up the equation, but so you have your product over your reactant, and that equals 1.7 times 10 to the minus 4, but really don't need to do that because we know that BKB is just minus log KB, which is, so it's 8.76. And again, here's a table of different KBs, and again at the top is the stronger bases, then at the bottom which are weaker bases. Okay, so let's take a look at this. Consider ionization reactions of a generic acid with water. You get this equation, and if you look at a base with water, you get this equation. Now what we're going to do is we're going to look at them and combine them. All right, and when you combine them, you can, when you add them up, you come up with these, you end up getting this equation here. And then what you end up getting, this is pretty cool relationship after you cross everything out, is that the Ka times the Kb is equal to Kw. The same Kw that we use for water, which is 10 to the minus 4. So, so this is going to be a powerful tool to use here, because this tells me is that if this is high, so if I have a high Ka or a strong acid, I'll have a weak base, and vice versa. And you can do the same thing with like you did with the PO and the pH, and you can get pKa plus pKb is equal to 14. All right, and again, what it tells us is that if you have something with a high K, which means a low pK means more acidic. That means this would be, if this was low, this would be high. That's because this has got to be constant, and vice versa. All right, and so we'll be using these in the next few PowerPoints to come up with numbers with our different acids and bases. So that ends it for this slide show, and I'll get it up on YouTube and get you the next one soon. All right, bye.